let's do some examples of different thermodynamic processes. These are what we call quasi-static processes because we do it very slowly. The pressure is constant throughout the cylinder. The volume is constant throughout the cylinder. And again, we've already derived that work is equal to the integral of pressure as a function of volume. But again, we can show this algebraically without using any calculus. Again, if the force is constant, which would correspond to a constant pressure, work is equal to F times the displacement. In this case, we're compressing the gas, so we're going to use a negative sign right here because we're applying a force onto the gas, okay? So it is doing a negative work in this particular case, all right? And we're going to make the same substitution we made before, that the change in volume is equal to the area times the change in distance. That's just the volume of a cylinder. The volume of a cylinder is area times the height. So we make this substitution for y right here. Here's a substitution for y, and that's going to become delta V over A. And now we're going to make a substitution for force. Pressure is force divided by area. So force is going to become PA. And just like before, our expression for work now becomes negative. F is PA. Delta Y is delta V over A. The A's cancel out, and we get work equals negative P delta V. All right? So for any type of isobaric process, iso meaning constant, baric meaning pressure. Anytime the pressure is constant, we can get a fairly easy relationship between work, pressure, and the change in volume. Okay? The work done by the gas is pressure times delta V. The work done on the gas would be negative P delta V. Then again, you get the same exact expression if you did it, with calculus. We've already demonstrated again that with the general form of work being equal to the integral of force as a function of displacement, that gives us the integral of pressure as a function of volume. What does this look like on a graph of pressure versus volume? Well, that's a rectangle. We did these isobaric expansions and compression already without actually calling them that. Because when we think about this, if the pressure is constant, okay? Oh, that didn't work. Let me try that over again. If the pressure is constant, we're going to remain at this particular level. We'll get a horizontal line, okay? And once again, according to what we said before, the work is equal to the area underneath the function, right? And in this particular case, if P is constant and we integrate over V, we just get delta V, where delta V is just the base right here. So this is just base times height for an area. Base times height for an area. And that gives us this nice work equals P delta V. Okay? So isobaric, this expression will work as long as our pressure is constant during the entire expansion or during the entire compression. Again, the pressure remains constant during an expansion or compression to be isobaric, okay? don't use this equation, work equals P delta V, for anything but isobaric, where the pressure is constant, okay? Because obviously, unless you've got this horizontal line, you're not going to get a rectangle, okay? And this is completely based upon the area of a rectangle. Now, the work done by an expanding gas in an isobaric process comes at the expense of internal energy, okay? Think about this. Again, we'll draw this graph. We got pressure, we got volume, and we're going from some initial point to some final point, okay? And then we're taking the area underneath this graph. Well, the problem is this. You know PV equals nRT, okay? If our temperature remained constant, okay, the pressure would actually decrease with volume. Rewrite this equation. P equals nRT. Now I'm going to put the volume on the other side. Look at this relationship between these two. Pressure is inversely related to volume. So to prevent the pressure from dropping, like it would in an isothermal process where T were constant, okay, as the volume goes up, to balance that, so pressure remains constant, the denominator is getting bigger, guess what the numerator has to do? The numerator has to go up too. So in an isobaric process, two things are happening. Volume is increasing if it's an expansion, okay? And temperature is also increasing. So for that to take place, I need to be adding Q, I need to be adding heat to the system to prevent the temperature from going down, okay? Now the heat for an ideal gas goes by 5/2 nR delta T, okay? Here we have 5/2. This, by the way, is for a monatomic gas. You know, like a noble gas, helium, neon, argon, and so on. There's a number of moles, there's a gas constant, there's a change in temperature. So Q for any ideal gas would follow this equation right here, where N is the number of moles. Cp is the molar heat capacity, okay? It's the amount of energy per mole per degree Celsius, and delta T, of course, is a change in temperature. All right? By the way, you'll see this expression right here. It says that the molar heat capacity at constant pressure is equal to the molar heat capacity at constant volume plus R. How can the molar specific heat be greater for constant pressure than for constant volume? Well, the reason for this is, again, think about our graph. Here's pressure, here's volume. If I look at the specific heat at constant volume, I'm moving up and down some line right here. I'm keeping the volume constant, okay, but changing the pressure by changing the temperature. So all I need to do there is add heat to change the internal energy. When I'm changing the heat at constant pressure, guess what? I not only have to add energy to change the temperature, but I also have to add energy to make up for the work that I'm losing. So that's why those two terms are different. So let's take a look. As we said before, for an ideal gas, Cp, the molar heat capacity at constant pressure, is equal to 5/2 R, okay? R is roughly 8.3. So let's do this in our heads. Multiply, we'll simplify this. Multiply 5 times 8, and we get 40 divided by 2. Doesn't this match very nicely? So we can see right here that the specific heat for a monatomic gas using the ideal gas law matches very, very well for helium, argon, neon, and krypton. And that's not surprising because when we think about these gases, they don't really interact with one another. Okay, there's not a strong van der Waals force between them. Okay, so again, that would be our expectation, that we would come very close to that value right there. Now, for diatomic gases, they behave a little bit differently. Okay, for a diatomic gas, Cp is supposed to be equal to 7/2 times R. Okay, so we think about this. 7 times 8 is 56. We divide 56 by 2, and we get 28. Hydrogen comes pretty close to that, but as you can see with the heavier gases, they begin to deviate more and more from that because of the intermolecular forces. All right. Let's do an example of isobaric expansion. I know an internal combustion engine is not a fantastic example for this, but we're going to use it here. It'll serve its purposes. What do we have? Approximate the power stroke of a 4-cylinder automobile. Okay, got to know a little bit about 4-cylinder automobile. There's going to be 4 different cylinders that are doing work at any time. It operates at a pressure expansion of 10 atmospheres. So we're going to say that the pressure is about 10 to the 6 pascals as it's expanding. Its volume change is 1/2 liter, and that'll be 5 times 10 to the minus 4 meters cubed. Remember, 1 meter cubed is equal to 1,000 liters. That's where that conversion comes from. If the engine is running at 3,000 RPMs, what is the total power output of the engine in watts and horsepower, and find the engine torque? We won't do engine torque, but we'll do power. Power is equal to the work done divided by the time. So we need to calculate the work due to each isobaric expansion. Work equals pressure times change in volume. And we need to find out how often one of these cylinders fires, okay? Given, 3,000 RPMs, that's roughly, 500 rotations per second. Okay, let's do this. So the first thing that we're going to do is calculate the time for one complete engine cycle, delta T. A 4-stroke engine, there are 2 engine revolutions per each rotation. So the engine will rotate twice for each power stroke that takes place, is what we're trying to say right here. So here, delta T is going to be equal to 2 divided by 3,000 revolutions per minute. Going to change 3,000 revolutions per minute to there's 60 seconds in a minute, and in every 1 minute, we get 1,500 rotations. So that gives me 0.04 seconds between each cylinder firing, okay? Now, we'll come back to that later. That's our delta T. That's our delta T in our power equals work divided by delta T equation. So we use that later on. Okay. Calculate the work for each expansion. Work equals power times delta V. We have 1,000 pascals. All right. We have 5 times 10 to the minus 4 meters cubed of volume change. And this is going to give us 500 joules. Okay. So every time the cylinder goes through its power stroke, it's going to give up 500 joules to the outside. Now we're going to calculate power. Power is work divided by delta T. There's our work. There's our time, 0.04 seconds. Okay. And that is 1.25 times 10 to the 4 watts. Okay. If you want to convert watts into horsepower, there's 746 watts per horsepower. So this particular engine operating at 3,000 RPMs will put out 16.8 horsepower.